Alright, today I've actually got something to share. Finally, I have a plan for what to present. So today we'll be talking about a particular question in a finals paper that I was doing, and I think this would be a good thing to try to explain, to walk through. So let's start. I use the highlighter for the first time. You're required to implement and optimize the storage and search. Remember, storage and search. So this too is the most important things we'll be looking out for today. Of multiple file sizes of 1 MB. So each file is a unique numeric identifier and is saved on disk using the ext2 file system. This is important, we'll walk through that later. The number of files is unlimited, let's say 10 million, but it cannot grow beyond the disk size. We want to optimize this file system to store and search fast for files by identifier. So we should use the methods under the file system implementation, etc. etc. So before we attempt the question, let's go through a bit of the background. So I mentioned the ext2 file system just now. Why is that so? That's because the ext2 file system has a really unique way of storing files. So let me use the rectangle feature. Yeah. Okay. The ext2 file system stores directory entries, which are items within a particular folder, via a linked list method. So let's say there's one item in the linked list. It's actually not linked list, it's more of an array that has it's more of an array that is just acting like a linked list because each item in the array has no set size. So normally they put the inode number here, they put a pointer to the next element, and then they put some item data like, oh, this, if it's a file, then they put like the file name, let's say name. Actually no, yeah, they put a file name like here, so name, and then they put some more stuff, etc. So this structure repeats over and over again. So they can put inode number, let's say it's 95, put a pointer to the next one, and oh, this one could be a directory, and then they could add more data. This could be another inode, so on. This could point to the next one, so forth. So this is how the ext2 file system implements having multiple files in the same directory. So two problems here. So storage and search. Firstly, storage. How do we store a new file? Well, in this system, that will mean that we have to find space to put it into the list so that our file can be part of this list of files within our folder. So this linked list will have an end, and so to get to that end, we have to go through the entire list. For example, here, jump to this, and then let's say there's nothing else here. Then we can insert something, we could insert like a new file entry here if let's say that's what we wanted to do. So we want to store by iterating to end. Then next issue is the search of files. Searching of files isn't just searching, we have to search by the identifier. And the identifier, in this case, is actually the file name. I made a mistake, it should be identifier. So not only do we need to iterate through every element to search for the file name, for the file identifier, we must also check each of these for the identifier. So we have to check each item's identifier. And so that brings us to the issues that we see in the first parts. So let's see, first, assume all files are stored in a single directory. What will be the main disadvantage when we want to add a new file, and what's the main disadvantage when searching a file by ID? Perfect, just what we were doing just now. So let's go back to this. This is a very simple illustration. There's only 3 items. But let's say there were 10 million files. Well, then your linked list would be a lot longer. So you'd have 1, 2, ... times 10 million. And then finally, you will have a blank space that you can put a new file. So the issue here, first of all, the main disadvantage is you have to iterate through the entire 10 million directory entries. And obviously this isn't very good because it actually grows linearly with the number of entries. And if you think about it, ON isn't a very good time complexity or like space complexity. Then for searching a file by ID, that's a lot worse. That's a lot worse, because not only do you have to iterate, you also have to search and like compare, which takes a lot more operations considering it's a numeric object. So search and compare these IDs. That would take way too long, especially with 10 million files, and especially because it grows linearly. So how are we gonna fix this? That is the next question, of course. Assume you have no restrictions in how many directories you can use, how would you mitigate the advantages shown in point A? So let's go back to the main issue. Main issue is there's too many files to search through. So this is too much. Too much. Ooh, my lights went out. So how can we reduce this number so that it's not too much? We go back to the starting point where this is all files in the same directory. But we no longer have a limit on how many directories we can use. So what if we broke down our 1 million folders, our 1 million files, into different smaller directories that each had a lower number of files? So let's say with a number x, let's say x is the number of folders or number of files in a folder. Let's let that be 1000. So instead of iterating through 1 million files, we only need to iterate through 1000 files before we get to the end of a linked list. That sounds good, right? So the first part is we split these files into folders. What's next is we also need to find which folder to put it in, because let's just say I have A, B, C, D folders, and I have like 1, 2, 3, 4, 5 files. I can say 1 goes here, 2 goes there, 3 goes here, and 4 and 5 go to D, etc. But when I'm looking for them again, how do I know where I put them? Where can we know where it goes? If you know CS, this is the perfect issue for this thing called a hash table, hash table. A hash table basically takes any input, let's say file A, and then it goes through a hash function, and then it becomes a hash. A hash is normally just a random numeric value, could be like n, that is unique. That's uniquely generated for each entry. It's not unique, but there's usually every value that enters the function will return a unique hash value. This is basically a way for you to convert data or file identifier into another shorter, more predictable number. In this case, a hash table it will normally convert something like, it will normally be a table, and it will convert your values A, B, C, etc. into indexes of a set range. So in this case, our set range is 1000 because we have 1000 different folders. Actually, no, it's not 1000. We have 1 million over 1000 folders because we have to split each of the 10 million files into 1000 folders. Folders of 1000 each. So through this, we have to find out this is 10,000. Hence, our hash table needs to map an item, a file, into a number between 0 and 10,000 and store that number in memory. And we can absolutely do that using a hash table. Remember, because This function is a static function. You just pass the file name in the file identifier, and it gets your index out. And so it gets your hash out, and this hash is mapped to an index. And since there's only 10,000 indexes, you can absolutely fit that within memory. So we can do that. And hence, part 2 of the solution is use hash table to map file to directory. So that is the solution to this part. We can use a hash table and directories to break this down into multiple folders to make it easier to find where to put the files. Next up, searching a file by identifier. Okay, I'm back. So how do we mitigate the disadvantages of searching? So this is basically the same as the previous solution. So what we want to do as well is use hash table to find the folder where the file is placed. And then using this, after finding the folder, we can just search through a lower number of files. And that's basically a solution to this one, because we can just search this smaller directory for the file that we want compared to all 10 million of them. I'll have a concession to make. I think the answer for this part could have been simpler and not involve hash maps, but I think I may have jumped the gun. It's fine, it's still a valid solution. Now, this part. We are allowed to use additional data structures to speed up the storing and searching of files. What data structures would you use to implement your optimizations? The default template answer was to use the approach that we did in question 2 or part 2 here. This was the optimal solution, which is to use a hash map to map your files into a folder. But they also talk about a hierarchy of folders, which I'll talk about now. So let's say we have each of this is a file. Actually, that's too big a file. Let's use a smaller file. Let's say each of this is a file. There's a lot of files, and then we split them into folders. So with this lower number of files within a folder, that's easier for us to search. However, we have to realize we also have a lot more folders with files attached to them. And so, at some point, searching through these is very time consuming as well. In addition, the hash map, even though it's only 10,000 entries long, in more extreme cases, it could be too large, or it could be unfeasible to put the entire hash table in memory, which would slow down the lookup by a lot. So what do we do? What we do is we put another layer of folders, and then we map these folders to other folders. This way, there's a drastic decrease in the number of folders from here to here to here. And there's a hierarchy of folders that we search to find the solution. So this is a very high level overview. Internally, it's just more hash maps, so you can envision how that works. So lastly, explain how your suggestions improve the storage and search times for file. Okay, originally, let's just go by the rubrics they said. Let's creating, maintaining, and using. In the original linked list method, what creating required on to get to the end of the list to add more. Maintenance requires I don't think there's a maintenance for linked list, so we just put it as blank for now. And using it, or like getting the data, searching for it, also requires you to iterate through all n things, where n is like 1 million, 10 million. However, your hierarchical folders has a lot less to worry about. So let's say we're working with just 2 layers. So we have hierarchy 1 splits into hierarchy 2 splits into file. That's a very bad illustration, I'm sorry, but yeah, imagine we only have two layers of folders. So what can we do with that? Let's say in the final folder there's only 1000 files. But let's make things simpler. There's 1000 items in each folder. In this case, that's 10 power 3. And so you only need to search through 10 power 3 folders 10 power 3 once because of the hash map. So using the hash map, creation is O log, in this case I think it's log 3, I'm not sure. No, it's log 10 power 3, so it's log 1000 10 power 7 or n. So this is a lot better than the original one, and using it is similar, log 1000 n. Okay, I'm pretty sure that this explanation is wrong. I still haven't wrapped my head around the answer yet, but you can see intuitively how much more efficient this is. I probably have to go more into the numbers on how hash map is O1 and etc., but my data structures course was quite a while ago and I forgot already. So, well, that's about it for today. Thanks.